Yeah.
So, welcome back for the second part of the CASA workshop. And so these two following talks are more on the topic of machine listening. And the first one is going to be by Jon Barker from the University of Sheffield. And it's titled Probabilistic Frameworks for Scene Analysis. So Jon Barker is a senior lecturer at computer science at the University of Sheffield and a member of the Speech and Hearing Research Group. His research interests include speech recognition by humans and machines, audiovisual speech processing, machine listening, and the application of machine learning to audio research. He's also very much involved in the CHIME machine learning project, CHIME or CHIME, not really CHIME, and also the Pascal CHIME speech separations challenge. So, thank you, Jon.
Thank you. Thank you for the introduction. So I think on the agenda my talk's called Probabilistic Frameworks for Scene Understanding. I've actually changed the title to Analysis because understanding is a kind of big word which I know nothing about. So I'll stick to analysis. So before I start, I want to just say what the scope of the talk's going to be. So when I talk about a scene here, I'm just talking about an acoustic mixture which is going to be made up of multiple sound sources. Analysis. By analysis, I mean kind of recovering high-level descriptions of sound sources from that mixture. So I don't necessarily mean forming a complete description of the entire scene. There'll be some task at hand, and from that task we've got to recover a description depending on the task. So maybe a large dog is barking in the distance, or a car is approaching rapidly from the right. For the purpose of this talk, I'm going to focus on the specific task of transcribing speech signals in complex acoustic scenes. Because this is kind of the bulk of what we do, is kind of robust speech recognition in our group. And we've been trying to apply ideas from acoustic auditory scene analysis to this problem of robust speech recognition. But at the end I'll try and draw back to some sort of more general framework which goes kind of maybe beyond speech. Also, a couple of quick words which kind of mentioned already. There's a couple of contrasting research goals which, depending on who you talk to, they might be motivated by different things. So an engineer might be motivated to design the most effective scene analysis systems. You're not bothered about human constraints. You just want to get the thing performing as well as possible. So such techniques might be auditory scene analysis inspired, but they're not necessarily CASA in the sense they're not computational models of auditory scene analysis. On the other hand, you have people who are directly modeling human performance, who are trying to build systems that directly mimic human performance, and they will try and adopt all the constraints from human physiology and psychology, and perhaps they are doing something which might be described as CASA. And then the evaluation of this is in terms of comparison to human performance. So I'm only kind of stating this because I'm not quite sure where I lie on the spectrum, but what I'd say is the stuff I'm describing now is perhaps ASA-inspired engineering rather than CASA. But I think it has got applications to CASA as well. So when we face this problem of understanding complex scenes which contain multiple sound sources, there's some questions I want to bear in mind throughout the talk. And these are kind of problems which I see as being kind of deep problems in this issues of this problem. So how can we interpret scenes which contain an unknown and a time-varying number of sound sources, where we have very few prior expectations about the number of sources and what those sources are? How can we ensure that computational cost stays bounded regardless of the complexity of the scene? So you might have an algorithm which works fine as only 2 sources in the scene, but how does it scale if you add in 3, 4, 5 or 6 sources? How can we interpret scenes which may contain unfamiliar sound sources? So I may have the task of listening for a dog barking, but there may be sound sources in the background which I have no models at all, which I have completely no knowledge. So how can we perform that foreground task if we don't understand the background? And lastly, I want to touch on this idea of how can we actually learn models of individual sound sources when all we're presented with is acoustic mixtures. So these are kind of some questions which we've been kind of considering, and I want to kind of just put those out there before I start the talk. So I'm going to start off by motivating by looking at some very simple scenes. I'll then introduce some sort of probabilistic models for analysing these scenes. I'll then show how these can be applied to robust speech recognition. And breaking with tradition, I'll end up by asking my own questions rather than asking for questions. So first of all, I want people to listen to this strange sound which I'm going to play, with no kind of prompting about what it might be, and ask people to give their impressions.
Where were you a year?
Oops.
Where were you a year ago?
Okay, so you hear some strange thing which you may or may not interpret. You may, if I asked you how many sounds were there, you may say there was 1, 2. Some people might even say they heard 3 different sounds. People might say they heard bird sounds or kind of whistling noises. Other people will say they heard speech. And some people might even recognize the utterance. How many people actually heard what was said? So yeah, a good number of people heard what was said. Okay, and a lot of people have heard it before, so they've been prompted and they got this prior thing. So what you heard there was an example of what's called SIMO speech. It was a stimulus which was kind of popularized by Robert Remez back in the 80s, working at Haskins Labs. And what you do here is you take some speech and you track the vocal resonances, the formants of the speech, the time, the frequency and amplitude of those things going through time. So you can see there's natural speech, it's got these 3 vocal resonances. You can track those, and then you re-synthesize the signal, which is just composed of 3 time-varying sinusoids. So everything else has been stripped out, you've just got these 3 time-varying whistles, which are these things here. So you look at a spectrogram of this, you now see these black lines which follow those formants. All the other detail of the speech signal has been removed. And in particular, the harmonicity has been removed. So there's no longer any harmonic structure. Okay? So if I play one of these individually, it just sounds like some sort of slide whistle. So you hear these kind of 3 tones, and if you look at them here, there's no particular reason that these belong together. I mean, they're doing different things at different times. There's no kind of principle which they are necessarily grouped. When you play the whole lot together, especially after you've been prompted a bit, you know.
Where were you a year?
Misses off the whole time. So they form this perceptual whole. So now how is this happening? So if you think about the classic account of auditory scene analysis, it starts off this kind of primitive processing stage and then this kind of schema-driven processing stage. The primitive processing stage is all about kind of signal properties and looking for continuation and simple laws which can group stuff together. If you look at the original signal going in, you can imagine how these things here can be tracked through time and appear coherent, fair enough. So you might see there's 3 different things. But what you actually hear is this speech. So some process on top is kind of regrouping those together back into a perceptual whole. And this has been governed by some model of the speech. So you've got some model of the speech which is trying to join those back. And because they all seem to fit that model of speech, you hear it as speech. So that's a reasonable enough account. So you can think, what might happen though if we then say have something a bit more complicated, and rather than having one SIMO speaker, have a more complicated scene. So listen to this thing here now. Oops. So if you listen to that, and I asked you what that was, now even if I tell you now that was 2 people speaking at the same time, and ask you to say what was being said, you'd probably find that extremely difficult. Okay. So some people will get a few words, but okay, so it's extremely difficult. So if you actually look at the kind of an auditory representation, this is kind of going for a gamma tone filter bank on a nerve scale, so it's something like the auditory periphery. This is what these things sounded like. So this is the first utterance, this is the second utterance, and here the utterances have been mixed together. Now the point here is that you can actually resolve most of the sinusoids in this mixture. They're all kind of present. So there's not really a problem of masking here. These things are sufficiently sparse that most of the stuff in here will appear in here or here. So it's not a masking problem. It's kind of a problem of how do you put the things together. So if you colour code this, you can see what we had is my dog Bingo ran around the wall, and again, where were you a year ago? And here's the 2 together. if you actually look at the bits where this is either matching to the first or the second, you can see basically you've got most of the structure there for my dog Bingo ran around the wall, and you've got most of the bits there for where were you a year ago, and most of the time these things are clearly resolved. So if you were to do some sort of primitive grouping on this, you might find these little bits of tone coming out. But what people don't seem to be able to do is to select from that and find the pieces which match one particular schema for one particular sound source. So you can imagine there's a computational problem there. You could go through there and you could try all sorts of different segmentations. But people don't seem to be very good at solving that problem. And we run experiments in an acoustic booth with people listening to hundreds and hundreds of these things, allowed to repeat these things as many times as they like, but they're phenomenally bad in actually trying to find utterances or even single words in these mixtures, even if they are very, very good at understanding individual sound wave speakers. So that's a bit of kind of background. So I want to introduce a kind of visual analogy now. So if you look at a picture like this, and you've got two things you're seeing, two pictures being mixed together, and if you spend some effort looking at that, you will probably be able to work out what they are. So you can see there's two animals there, and you can start to pick them apart. But the problem you're having here is that it's not the information that's been lost which is the problem, it's the reconstruction. It's trying to put back together the right bands that go with each other. If I give you a clue by colouring it, now hopefully you should be able to focus on the red thing and see a cat very clearly, focus on the green thing and see a dog very clearly. So the problem you were having before wasn't necessarily the information that was missing, it was this problem about how things go back together again. So given this kind of colour cue, you can now group those other things together and you can see the cat quite clearly. But before, without the colour cue, that problem was quite difficult. But you're using kind of top-down knowledge of what cats look like, and you're being able to search through those bands and put that thing back together. Okay? So these grouping cues are helping you to kind of solve this problem of organising these fragments. So now I want to kind of consider a couple of kind of computational approaches to understanding complex mixtures. So one approach would be what you might call model combination, which is taking a model, a statistical model of all the sources in the scene. So you've got some, say you've got some sort of speech model for Q, you've got some states of that model which lead to some observations. We've got some noise model, which some states which leads to some observations for that model. And then those things two get mixed to make this noisy mixture. We observe the noisy mixture, and our task is to try and infer what either Q of X is, or both Q of X and Q of N. Now, if we pose that as a problem, we can say, we're trying to find the particular Qs of X's and Qs of N's, which maximizes probability. What's the probability of Q of X and Q of N given Y? And we can do that if we search over all possible QNs and QXs. So we've got two talkers, we have to go through all possible states in the speech of one talker and the other talker. And we can try every single possible combination and find two sets of states which make that mixture. And it becomes a very complicated search problem because the search space is in all the states of Q of N and Q of X. If we're interested in Q of X, we have to kind of integrate over the states of Q of N, but we've still got this factorial problem where we're searching over Q of X and summing over Q of N. And that's all very well with two sources, and how is it generalized to more sources? So if we add in more sources, even if we've got models for the sources in the environment, and we know what those sources are, to try and make inferences, we've got to now sum over this combinatorial state space of all the possible sources in the environment. And this can quite quickly become computationally intractable. It might not be a nice approach to the problem. So that would be a kind of a way of trying to understand the scene by combining models of all the possible sources available. So I want to kind of motivate a second way of looking at it. Rather than trying to make an exhaustive description of the complete scene from all the individual sources available, we'll introduce a segmentation and say the problem is just to understand the foreground while ignoring the background. Okay? So we have some mixed signal like I saw before. If I know how this thing's segmented, I can introduce what might be called a segmentation mask, which is just a binary mask which is going to say ones or zeros, picking out the bits which belong in the foreground. If I then pose that mask on the image, like this, And now I can try and recognize this thing here, which has come through the mask. Now once I've been having this masked image, I don't actually need to know about the background anymore. The background's been masked out. What I need to know about is a model for the foreground. Okay? So if I was given magically by someone this mask, I wouldn't need to know anymore what these other sources were. I could just have a model for that foreground and recognize that thing. And the same can be said for the sign of speech example. If I got the mixtures, I can compute some mask if I could. I could place it over the mixture. I'd see the parts of the foreground coming through, and I could match that to my model for sign of speech. The task be complete. Now you might say that's all very well for things like sign of speech, which are totally sparse, and this kind of artificial thing where I kind of banded the image anyway, so it doesn't actually mix. But how does it actually apply to real acoustic mixtures? If I look at something like real speech signals, so here's two real speech signals. I've got an utterance here, being green at T5, please, set blue with A8 again. These two acoustic signals are being mixed. I've computed these representations, and I've color-coded them to pick out regions where either matches more closely to the blue one or to the red one. And what you can see through the color coding is that most parts of the blue signal are coming through here, and features in the red signal are coming through here. So speech is quite sparse. Now it's quite peaky. If you mix it into a background, plenty of stuff comes through, pretty much undisturbed. So if you apply the right mask, you'll be able to recognize that signal from the bits that remain. So that kind of motivates this idea of kind of missing data speech recognition. So rather than try now to have models for all the sources and describe the scene in terms of those models, we now have some mixture which is given to us and some segmentation which is given to us. And the actual speech, or the source we're interested in, is associated with the mixed signal and the segmentation. And then from that we try to infer the states of the speech model. Along the way we had to make some sort of assumption here that the actual statistics of the speech signal, or the target signal, given the mixture and the segmentation, are independent of the noise. So that's to say that once you've got this mask, you no longer need to know what the noise is. So this is approximately true, because in places where the speech signal is dominant, it dominates the mixture to such an extent that the variation of the noise doesn't actually contribute much to the mixture in the log space. So we can pretty much say that what we either see is the clean signal, which is not influenced by the noise, on the masked regions. We've seen some noise, and this clean speech signal lies at some point beneath that signal, but doesn't actually influence the noise. So once you introduce the segmentation, you can pretty much throw away any idea about noise models. But the problem is, obviously, in real life, we're not given this segmentation. No one tells us this is the foreground and that's the background. If you were, the problem would be trivial. So if you are, if you cheat and actually work out what the mask should be before mixing these two signals together, you can take the noisy signal, you can take the mask, and you can apply these kind of models and get kind of superhuman speech recognition performance. So the problem is we're not actually given these segmentations. So let's skip over this. We're not directly given the segmentation, we don't see that. But we do see some features in the signal which can inform what possible segmentations might be. So these are basically what we might call the primitive grouping rules. So these are things like the pitch and the continuity of the signal. These tell us what segmentations might be plausible and what segmentations are not plausible. They give some space over what possible segmentations might look like. So now, rather than knowing the segmentation a priori, we have to kind of consider all possible segmentations. But the probability of segmentation is given these cues which help us to determine whether segmentations are possible or not. So it's not a case of having kind of data being present or missing. We no longer know precisely which bits are present and missing, but we've got some knowledge of that, which is coming from these observations, like pitch. So how does this kind of relate to auditory scene analysis? So this segmentation model, this is what you might be called the primitive grouping component. This is telling you whether something is a plausible segmentation or not a plausible segmentation. And it's using observations from things like pitch and onset, which kind of Bregman would call the primitive grouping models. And this model is independent of the sources. It doesn't depend on whether you've got noise or whether you've got speech or you've got whatever the sources are in the environment. This model here is independent of those sources. It applies equally to all sources. And then we've got the second part, which is this kind of scheme-driven processing, for which we have models of the targets we're looking for. So this, for this part, we do need to know what we're looking for. So this thing just kind of is a generic, if you like, a generic cutting up of the scene into pieces and tells us what segmentations are possible, which ones aren't. And this one then tries to reconstruct those things, given the knowledge of some target. So now the problem of the kind of interpreting the source we're looking for becomes one of searching over a load of possible segmentations, and for each segmentation trying to match that to the models of the target. So we're now going to kind of perform some sort of maximization task where we're looking for what the possible targets are and also the most likely segmentation. So it's a kind of two-way kind of decoding where we're looking for, if it was speech, we're looking for some sequence of words, and we're searching over a space of possible foreground background segmentations. So one particular version of this model that we've done is what we call fragment decoding. So in this model here, you've got to know, if it's a segmentation, what's the probability of some segmentation? So in our simplest model of this, what we do is we say segmentations are either invalid, they've got 0 probability, or they're valid segmentations and they've got equal probability. So that's the kind of simplest model we can apply. And then we define what might be a valid or invalid segmentation by identifying fragments in the source, in the mixture, fragments which belong to one sound source. And then what we're going to say is any segmentation that puts, which is made up of a bunch of fragments in the foreground and a bunch of fragments in the background, is going to be a valid segmentation. So if you look at an acoustic mixture, it might be very difficult to segment this into a foreground or background without knowing what the sound sources are in the mixture. But by using kind of things like harmonic relation, common onset and common offset, you can find locally coherent pieces. Pieces in the mixture which you have a strong belief that these things here all belong to the same source. So in this region here, these things are grouped by kind of harmonicity. So that whole region there belongs to the same source. I don't know if it's part of the background or part of the foreground, but I know that belongs to one source. Once I've got those fragments, logically, if that all belongs to one source, it can't be part in the foreground or part in the background. So it must either be assigned to the background or the foreground. Therefore, the number of valid segmentations I can make is just different labelings of these fragments as either foreground or background. Okay? So I've got a bunch of fragments here. Some of these are part of my target speech source. All the others are part of the background. So the number of segmentations I can make is actually quite limited. So these fragments are constraining the kind of search space over possible foreground-background segmentations. So then our kind of model of what's kind of scene analysis from a perspective of the problem of looking at speech recognition would look something like this. We'd have some mixed acoustic signal. We'd have some sort of block called primitive CASA, which is going to be doing kind of spectral analysis, looking at harmonics and harmonic regions, and trying to segment this representation into locally coherent regions, where each region either belongs to the foreground or the background. We don't know which. And then we've got some fragment decoding thing, which takes models of the target source. And it's going to search over possible segmentations which are consistent with these fragments and the interpretation of the speech string. And as an output now, it's going to come out with the word string that's been set according to the models and this kind of foreground background segmentation. So what we're not doing is we're not trying to explicitly find the foreground first and recognize what's in the foreground. We're searching over a possible search space of plausible foregrounds, at the same time as looking over this possible search space of the word strings. So, I mean, the way this is implemented internally is just like, here's a possible set of fragments. From the set of fragments, each of these fragments can either be foreground or background. So I can then generate a whole set of foreground-background masks. And for each foreground-background mask, I say, well, this is the foreground. Here's my speech decoder. I can then search over possible word strings, so this is the foreground mask. I then can take the highest scoring hypothesis at the end of this process. We don't actually implement it like this internally because here you've got n fragments, you've got 2 to the n possible segmentations still a very large number of segmentations. But because a lot of these segmentations share features in common at different times, you can have a kind of branching and merging tree structure which searches over these segmentations in a very efficient manner. So how does this kind of work as a model of scene analysis? So you've got auditory periphery, and we've got this kind of primitive grouping rules now. But these grouping rules are being kind of represented as these kind of segmentation constraints. Constraints are saying whether something is a good segmentation or a bad segmentation. And then we've got some sort of target model selection. So we might have some sort of source models. But rather than having to describe the whole scene now, we're just picking out the source model for the thing we're interested in. So we might have an attended source, the segmentation constraints. And then a scene analysis is then searching over segmentations and interpretations of this source to come out with a foreground model description. So it's no longer the kind of symmetric thing which is trying to look at all the sources at once and describe the entire scene. This is kind of basically asymmetric thing where we are basically taking the foreground model and some model of what could be foreground, could be background, and just trying to describe that single model. How much time have I got left?
About 5 minutes.
5 minutes. So, I mean, we've applied this to various tasks. So one task is this kind of grid corpus speech recognition task, where we've got these very simple references, things like bin blue at A5 again, or bin red on Z2 again. They've all got this letter digit part. Then we have different speakers of this, who are set like this.
Set white with P2 soon.
Set white at P2 soon. And then you can mix 2 speakers together and
Bin
Play
white
green
at
by
K2,
S4
please.
now.
so you get this kind of complex mixture of two speakers. And one of them is saying the word white, and the task is to listen to the person saying white and report the grid reference that person says. Ignore the video, because in the tasks it's just audio only. Video.
Bin
Play
white
green
at
by
K2,
S4.
So the person saying white said K2 in that instance, and you listen and you have to report the K2. So that's the kind of the task. And if you look at listening performance on this, what you can do is you can mix 2 speakers of different gender, the same gender, or even the same talker speaking against themselves. And you can vary the SNR of the target, so the target's either louder than the masker or much quieter. And you get performance curves like this. So if they're different genders, listeners are very good at this task, and they get about kind of 95% right, going down to about 80%. If they're the same gender, they get these performance drops. And if the same talker, it drops much further. Interestingly enough, I mean, the worst performance for the same talker isn't at minus 9 dB, where it's loudest. It's at about here. The reason here being is that that is the level where things are most confusable. Both the background and the foreground have the same level, so it's very hard to unmix the two. So this is kind of saying that actually, even though the background is getting louder and louder here, the task becomes easier because it's easier to attend to the quieter thing and not get confused. So there's a kind of informational masking aspect in the task. And you look at, this was run as a speech separation challenge sponsored by the Pascal network in 2006, and there's a bunch of computational techniques, some inspired by CASA and some just trying to kind of brute force the thing and see how well they could do. Listener performance overall is that red curve there. This kind of fragment decoding approach is this green curve here, which to some extent kind of mirrors the trend of listener performance, although at a much kind of lower level. And this blue curve up here was a team from IBM, which did the kind of full model combination approach, applying all the kind of tricks of model combination. They got explicit models for both sources and combined them. And interestingly, they're kind of getting this curve here, which actually lies above human performance. And if you start looking in particular at when you've got the same gender condition, so two speakers of the same gender, the listeners are kind of dipping down at 0 dB. If you make explicit models of both sources, you can get this extremely high performance, which is well above what humans can do. So, I think this kind of tells us something about maybe what listeners are or are not doing. So I think this is extra evidence that they're not actually making explicit models of every single source in the environment. They're doing something, they've got a simpler model of the background, and perhaps just a masking model. So, I've kind of put that approach, this fragment decoding approach out there. There's a lot of things in it which are quite deficient. One question that strikes me is how do you effectively interface the grouping rule stage of ASA and the schema-driven processes? So you've got these rules like harmonicity and onset and offset, and often these are posed as kind of deterministic rules, but they have to be interfaced to this kind of probabilistic approach to matching models. Even in our scheme, we've got these fragments, but the fragments we're using are binary in a sense that they are discrete. They're either in the foreground or in the background, and they are discretely defined. That seems like too much. That's not soft enough. You can't, in practice, necessarily find nice, coherent, discrete fragments. Another question is how much information about the background is used during interpretation of the foreground. So, in the fragment decoding approach, basically there's no background model. The background model is kind of implicit in the segmentation model, but there's no explicit background modeling in there. Whereas in a kind of full model combination approach, you can, you take a model for the foreground and a model for the background, and you search through them trying to find the one that best describes the mixture. That's kind of the other extreme. And if you are going to take this kind of segmentation approach, what should you do in situations, as an engineer maybe, where you do happen to have strong knowledge about the background? So if you're doing a speech recognition task, often you can look at the times before the person started speaking, measure the background, and make models of that background. And if you've got models, statistical models of the background, shouldn't they be used in decoding the speech in the foreground? And that pretty much wraps up what I want to say.
So we are running a little bit behind schedule, so I would propose that we put the questions in the debate right after the next talk, if you don't mind. So in that case, I would thank you. And